Hello and welcome to this session on recall and precision. Both of them are nothing but evaluation metrics which help us identify how good a classification model is. Now, a lot of people wonder, why is there a need of any other evaluation metric when we have accuracy which is so intuitive and so simple to understand. So in today's session, we'll try to understand the precise need of both these evaluation metrics, and we'll try to do this using a live case study. Now, before we go there, I want to make sure that we know one thing which is very important, especially in this case of recall and precision. So for those who have not heard anything like unbalanced data set, it's your time to understand more about it. Now, what is unbalanced data set? So unbalanced data set is a data set where the target variable or the y variable has disproportionate levels in that. Now, what do I mean by that? So let's say I have this data set, and I'm talking about a binary data set where my target variable has just two levels, either a 1 or 0. So let's say we have this data set with few independent or predictor variables, let's say 4 of them. And then we have a target variable, which is y. So these are predictor variables, and this is a target variable. So what I mean by unbalanced data set is, so let's assume this data set is about credit risk. So given the characteristics of a person who is coming to take a loan from the bank, let's say X1 is age, X2 is income, X3 is the amount of loan, X4 is probably the purpose of the loan, we'll have whether that person would default or whether that person will not default. So in a typical situation of credit risk modeling, people who are defaulting are far lesser than people who are not defaulting. So if 1 corresponds to people who are defaulting, and 0 corresponds to people who are repaying the loan back, number of ones are far lesser than number of zeros, which means that in this data set, I would have far lesser ones than the number of zeros. So this is what unbalanced data set is. On the contrary, a balanced data set would be when I have an equal proportions for both 1 and 0, or at least very close to equal proportion. So I would have 50% of ones, and I'll have 50% of zeros. So very close by to each other. Or maybe this can go on to 44, 45, and this can be 55. Still, they're very close to being called as balanced data set, as opposed to this unbalanced data set, where in a typical case of credit risk, I'll have around 90-95% of people who are repaying the loan back. So I'll have around 90-95% of zeros, and I'll just have around 5 to 10% of ones in the data set. So this is highly unbalanced data set. Now, let's get to the example and try to understand precision and recall with this understanding of unbalanced data set. So here's the data, the same data which we were talking about, credit risk scoring. So given these predictor variables, which are age, gender, employment, type of employment, house, again, the type of housing in which that person is living, whether it's a free accommodation, whether it's own house, whether it's a rented house. And then the amount of next variable is the credit amount, the amount of credit which has been taken from the bank, for the duration the loan has been taken, and for what purpose the loan has been taken. These are all my X variables. So I have 7 X variables from X1 till X7. And then this is a Y variable or a target variable. So for every characteristic, I would have a risk involved. So for example, if a person is 30 years of age, she's a female, this is the employment category, and she owns the house, there's the amount of credit she has taken, and for 36 months, and this was a car loan. This lady repays back, and thereby we have entered a 0 against her name or against her characteristics. If I take another example from this row number 36, I see that for all these characteristics, with all these characteristics, this lady has defaulted, and thereby I get a 1. Now, the typical behavior of this data set is, that I get far more ones than the number of zeros. So if I take the total number of row items, I have 50 row numbers, out of which I just have 8 defaulters, which means the proportion of my data set is number of ones is 16%, whereas number of people who are repaying back, so number of zeros, is 84%. Highly unbalanced data set. Now, with these data sets, we need to advance to other evaluation metrics like recall and precision. So we'll exactly see how this works. Now, this data set has been divided into train set and test set. Train set is 70% of the complete data set, and test set is 30% of the complete data set. Using train set, I have made the model already, and using that model, I have done a prediction with the resultant of that prediction is there in this column I, which has been annotated as predicted risk. So now for every row in the test set, I have the actual risk and I have a predicted risk. So for example, these top 3 rows have been predicted perfectly by my model. whereas this row has been incorrectly predicted, and so on. Now for this y and y cap, I have a confusion matrix. Now, if I count these risk and predicted risk, and I enter the relevant values in the true positive, false positive, and false negative and true negatives in this confusion matrix, I would get 1 true positive, I would get 2 false positive, I would get 1 false negative, and 11 true negatives. Now, for those who don't know how to make confusion matrix, they can probably go back and check my other session as to how do we calculate or design this confusion matrix. Now, moving on, with this kind of a confusion matrix, the accuracy what I get is nothing but 1 plus 11 over 15, which is 80%. Absolutely fantastic accuracy, isn't it? Accuracy of 80% means my model is doing really good. But I'll give you a very dirty trick to bump up this accuracy. Instead of this model, which is predicting these values for my risk, what I'll go on to do is I would probably make a very simple model, and I would just enter all zeros. So I would just enter all zeros instead of making this model. So if I do this, so let's say this is my model 1, and this is my model 2, where I am predicting everyone to be a non-defaulter, and thereby I'm giving loan to everyone. So this is my second strategy to model. My first strategy is, so let's kind of write this down in this sheet. So this is my model 1. This is my model 1. And let's say this is my model 2, where I am predicting everyone to be a non-defaulter. Now, what would be my new confusion matrix according to this new model? My new confusion matrix would be my true positives would be 0, my false positives would be 0, my false negatives would be 2, and my true negatives would be 13. And now if I calculate the accuracy, it is 0 plus 13 over 15. Fantastic. With a little dirty trick and a much simpler model, I'm getting much better accuracy, isn't it? But let's kind of just review what we have done here. So what we did was with model 1, we were getting an accuracy of 80%, but with model 2, we were getting an accuracy of 86.7%, almost 87%. Now, from business perspective, we are not making any effort to identify defaulters, which means the strategy is bad. Because the whole concept behind the loan industry is they want to correctly and as accurately as possible want to identify the people who might default on me. And thereby, I want, or I don't want to give loans to these people. So this turns out to be a bad strategy from business point, but my accuracy somehow increased. So this looks like a big contradiction between business reality and evaluation metric, isn't it? Which means my accuracy is somewhere flawed. And this is where exactly accuracy as an evaluation metric fails miserably. And where does it fail miserably? It fails miserably in cases of unbalanced data set. Since my data set was unbalanced, I had more number of people who were repaying back. So I thought, let's tag or annotate or predict everyone as a non-defaulter, due to which my accuracy bumped up. But that very small proportion of defaulters, I left them alone. And I left them to loot my bank. So let's try to fix this by creating some kind of a better metric, because of course accuracy seems to be incapable of capturing the situation. Now this is where I want to introduce the next evaluation metric, which is recall. So recall helps us in this scenario as an evaluation metric. Now, if we carefully see what our intent was, okay, in this kind of a business scenario, my intent was to build a model which is able to identify or predict all the defaulters. Or if I just talk at the data level, I wanted to identify all these ones very, very accurately, which essentially means that I want to maximize the count of TPs as compared to the count of FN. So I want to maximize the true positives as compared to false negatives. This is the basic business logic which I want to follow. Now, if I just try to convert this into mathematics, essentially, I want my TP to be as high as possible. Now, if I put it in a percentage perspective, I want this number of TP over TP plus FN. I want to maximize this proportion. And this ratio, what you see over here, is nothing but my recall. This is that metric. So recall, if I just want to make it a simple English, in English language, if I want to put it, this is nothing but out of total positives, how many could be identified by the model? So this is the question which recall is answering to me. So out of these total positives, which actually exist in the data, how many of them were correctly identified by my model? TP over TP plus FN. So now, if you look at that confusion matrix we were just seeing a little while ago, 0, 0, 2, 13. If I see the accuracy, it was 13 over 15. But if I see the recall, it is 0 over 2. Absolutely abysmal, 0%. So I fail miserably on recall value. And thereby, my model is not doing a good job. So I simply strike off model 2. Now, I have a different strategy. Okay, me being absolutely lazy and a weird fellow, I have a new dirty trick in my mind. Okay, I want to kind of fool the system with this new trick without doing much of work. So I'll make another model. I'll make another model, a very simple one, where I'll say that let's mark all of them as ones. Let's say all of them are defaulters. Now, business-wise, upfront, we know business-wise, this is absolutely weird. We cannot mark everyone as defaulter. This is huge loss to the business, because if we are marking everyone as defaulter, we cannot give them the loans. And thereby, we ignore a lot of revenue for us. So this could be a huge opportunity which we have missed to identify, because we are targeting all of them as defaulters. And this is all because of my pure improper modeling. But let's say I do this, and with this, let's try to enter the numbers in my confusion matrix. So my TP would be 2. Just do a quick math and or a quick recall of your confusion matrix, and you'll identify why I am entering these values. So my TP would be 2, FP would be 13, false negative would be 0, and true negatives would be 0. And now, if I see my accuracy, it would be 2 over 15. If I see my recall, which we just developed a little while ago, if I see my recall, it would be TP over TP plus FN would be 2 over 2. 1. Wow, 100%. Absolutely phenomenal, isn't it? We did a great job. But again, business-wise, we are giving a very weird logic. So now we need to refine further, and we need to identify more ways to fix this. Now, with this new model, model 3, I already know that recall alone cannot work well in case of an unbalanced data set. I need to have another metric. Which kind of helps me resolve this problem. And this metric is nothing but precision. And what precision says is, that out of the total identified true positives by the model, how many are actually true positives? Which means out of all these predicted true positives, how many are actually true positives? So if I write this equation, this goes on to tell me true positives over true positive plus FP. And plugging in the values, I get 2 over 15, which is nothing but 13%. Absolutely low. A very, very bad indicator for my model. Now, if I need to summarize, what I get is that my model 2 failed because of low recall and my model 3 failed because of precision. So essentially, if I want to fix a good evaluation metric in case of an unbalanced data set, it turns out that I need to do a proper trade-off between recall and precision, which means out of these and these, I need to have the maximum numbers in this box or in this quadrants of true positives. So there's always a trade-off between recall and your precision for the best fitting classification model. So I hope you understood why we need to have some better metrics when we already had accuracy as a very simple, sweet, and quite intuitive evaluation metric.